Hello everyone. Today I'm going to go over Friday's assignment, Thursday/Friday's assignment. The first is the AP page 30, number 79 problem. Let's take a look at this. The correct answer here was A, but let's see why. So here it says the graphs of the derivatives of the functions f, g, and h are shown above. Which of the functions f, g, or h have a relative max on the open interval from a to b? So remember, a relative max is going to occur when our function changes from increasing to decreasing. But we're not given the graphs of the function, so we have to rewrite this. So in other words, this will occur when our derivative changes from what to what? Positive to negative. So let's see where this happens. All right, so for our first graph here, our first derivative, this part right here, our derivative is negative. It's still negative, so that's not going to happen. It's negative all the way up to here. So right here we would say f prime of x is negative. And then over here, oops, just going to here, it's positive. And then looking below, we're negative again. So our derivative changes from positive to negative right here. So that looks good. For g prime of x, our derivative is negative here. And then our derivative is positive here. So it only changes, our derivative only changes from negative to positive. So g prime, or g is out. And then for h prime of x, our derivative is positive everywhere. So that's not going to happen. So that's why it only happens for our function f only, because that's the only derivative that shows that it's changing from positive to negative. All right, before I get to the assignment, let's go over the two homework problems, 13 and 16 from page 215. Let's go over number 13 first. All right, in 13, we're designing a poster. So we're designing a rectangular poster to contain 50 square inches of printing with a 4-inch margin at the top and bottom and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper use? Let's go ahead and draw a little picture here to help us. So let's say we're going to put a border here. We're going to be 4 inches from the top and the bottom and just 2 inches from the side. So we know this part right here is 4 inches, this part right here is 4 inches, this part right here is 2 inches, this part right here is 2 inches. So I'm going to go ahead and call this length right here x, and I'm going to call this length right here y. So the area of the poster is 50 square inches. So excluding the frame here, we're just going to say 50 is going to equal x times y. And we may need that. So we're trying to minimize the area as we're trying to minimize the amount of paper used. So we're going to call this the area of the poster plus the frame. So that's going to become x, and then we have 4 above, 4 below, so we're going to have an x plus 8. And then we'll have a y plus 2 plus 2, so it's going to be a y plus 4. But I want to get all of this in terms of one variable, so why don't we replace the y? So that means I'm going to go back over to this formula here and solve for y in terms of x. So y is going to equal 50 over x. So now my area in terms of x is going to become x plus 8 times 50 over x plus 4. Then I could go ahead and distribute. We're going to get 50 plus 4x plus 400 over x plus 32. So we could say that this is 82 plus 4x plus 400 over x. All right, so now we're just going to continue with finding a prime of x. Hard part's over, right? Coming up with the formula here. So that's just going to give us 4. And again, we can think of this 400 over x as 400 times x to the negative first. So we're going to get negative 400 over x squared. So minus a 400 over x squared. Then we'll set that equal to 0. I'll just say 4 will equal 400 over x squared. We can multiply both sides by x squared. So 4x squared is going to equal 400. X squared is going to equal 100. But in this case, since it's only, since we're dealing with dimensions, we only want positive only, so x is going to equal 10. And our derivative is undefined when x is 0, but x needs to be greater than 0. All right, so now what we could do is the second derivative test for extrema. I always like to write out that I'm using this. All right, so now we'll say a double prime of x is going to equal, if I'm looking right back up here, that's going to be a 0. And then we can think of negative 400 times x to the negative second. So then this becomes a positive 800 over x cubed. And we'll say a double prime of 10. Well, that's still going to be positive. So our function is concave up everywhere. Therefore, we have a relative min at x equals 10. So again, the question was, what overall dimension? So all we're after are the dimensions. So we'll write this out. All right, so I already know x is 10 inches. Y is equal to 50 over x, or we could, since we already have them in terms of x, so that means the width of the poster, that's going to be the x plus 8. So that's going to be 18 inches. And then the length was y plus 4. Well, y is 50 over x, so 50 over 10. So we'll say 50 over x plus 4. That's going to give us 9 inches. So we'll answer this now. So this is just our calculations for this. So now we'll say the overall dimensions that will minimize the amount of paper used are 18 inches by 9 inches. All right, let's take a look at number 16. Here we are again designing a can. What are the dimensions of the lightest open top, so notice there's no top on this, right circular cylindrical can that will hold a volume of 1,000 cubic centimeters? Compare the results here with the result in example 2. All right, we did a similar example. I don't know if that was... Yeah, it was very similar. So we can compare this with what we did in our example 3 off of that little half sheet. All right, so again, let's go ahead and draw a cylindrical can here. Again, the difference here is that there is no top. So that does not come into play when we're talking about whether, I believe it should be surface area that we're going to need again here. Because again, if we go back, we're talking about material needed here, so we want to try to minimize the material that's used here. All right, so again, we're just going to write this out, fill in some dimensions here. So we have our radius, and then we have our height. So again, the volume of this is 1,000 cubic centimeters. The formula for volume of a cylinder is pi r squared times the height. So we could say 1,000 equals pi r squared times the height. But again, we want to minimize surface area. So the formula for surface area is equal to pi r squared, not 2 because we don't have the area of the top, just the area of the bottom base here. So there's our pi r squared, and then remember as we roll this out it becomes a rectangle, so it's the circumference 2 pi r times the height. Well, I want this all in terms of r, so if we come back over here I'm going to say h is equal to 1,000 over pi r squared. So now s of r becomes pi r squared plus 2 pi r times our height, which is 1,000 over pi r squared. Then I could simplify this, so we get pi r squared. We're going to get 2,000 over r plus. And then we'll find our derivative. So s prime of r is going to become 2 pi r, and again this will become a minus 2,000 over r squared, because we could think of that as 2,000 times r to the negative first. All right, so let's ask ourselves those two important questions. Where is s prime of r equal to 0? And then it's 2 pi r. We could say equals 2,000 over r squared. We can multiply both sides by r, or rather r squared, so we'll get 2 pi r cubed equals 2,000. So pi r cubed should equal 1,000. We'll still divide by pi, so r cubed is going to equal 1,000 over pi. So r is going to equal the cubed root of 1,000 is 10 over the cubed root of pi. And that we were actually getting from our example 3. The radius came out to be exactly that. Whereas s prime of r equal to 0, again when r is equal to 0, but r needs to be greater than 0. So let's go through and do our second derivative test. All right, so s double prime of r is just going to become, looking at this right here, 2 pi. And again, if this is minus 2,000 times r to the negative second, we're going to get a positive 4,000 over r cubed. So now we would say s double prime of 10 over the cubed root of pi. That should still all be positive. So our function is concave up, and we would have a relative min at r equals 10 over the cubed root of pi. Again, we're just looking for the dimensions. So we know our radius, what our radius is already. So all we have to do now is go back and find our height. So if you recall, our height was 1,000 over pi r squared. So this becomes 1,000 over pi times 10 over, I'm going to write it as pi to the 1/3 instead of cubed root of pi squared. So this becomes 1,000 over pi times, we get 100 pi to the 2/3. So in example 3, this is where I went back and said, well, this is 3/3. We'll put that over 1. That's times. So now I get 1,000 over 100 pi to the 1/3. So I get 10 over pi to the 1/3 cubed root of pi. So my height and my radius are exactly the same. So the dimensions, that will make the lightest can are when the radius and height are both equal to 10 over cube root of pi centimeters. All right, so we're not going to do anything new today. I'm going to give you guys 4 review problems. This is posted as a separate PDF. And then on Friday, I'm going to give you a team assignment over worksheet 4.4. So hopefully for the Zoom, I should be able to let you guys just kind of work together. If you all join Zoom during class time, you can absolutely do that. So take care. Let me know if you have any questions. I'll give you more information on how my remote students can work together on the team assignment.